This morning, I had a bowl of plain Greek yogurt and toasted muesli for breakfast. I could have had a plain bagel with mashed avocado, or I could have had nothing at all, but I had the yogurt and muesli. I know, damn millennials and their hipster breakfast food. But also, who cares what I ate for breakfast? Well, perhaps the universe does. Imagine that, after breakfast, I dutifully went to the lab to perform some quantum physics experiments. The results of the experiments obviously depend on what I do in the lab, but they shouldn't depend on what happens outside of the lab, right? I mean, why should laser light bouncing around through crystals and mirrors care what the current value of the S&P 500 is, let alone what I had for breakfast? The conditions under which an experiment is performed are called its context. In practice, the contexts we consider are very limited to a few settings on the devices in the lab. But maybe the temperature of the room is important. Were the lights on? Was the door open? Especially when things go wrong, which is more often than not, the context is where you look for answers. But some parts of the context are so far removed from the experiment that there is absolutely no way they could affect the results, such as that delicious muesli. Did I mention it was toasted with a hint of maple and paired with a pot-set Greek yogurt? A theory is a set of mathematical rules that make predictions about the outcomes of experiments. Most theories automatically rule out most contexts simply by ignoring them. Dependence on other contexts are ruled out by experimentation. If there is no possible experimental arrangement in the lab that can distinguish what I had for breakfast, then the theory shouldn't make reference to that context. Think of it as an application of Occam's razor. Indeed, quantum physics makes no mention of breakfast choices. As successful as quantum physics is, it is merely an operational theory. It's like a lab manual with instructions about the preparations and expectations of experiments. It's remarkably accurate, allowing us to engineer materials and devices which form the basis of all modern technology. But it doesn't tell us anything about reality, and that bothers a lot of physicists. What is reality? Nope. There's no way we are going through that philosophical minefield. Let's focus instead on scientific realism, the idea that a world of things exists independent of the minds that might perceive it, and it is the world slowly revealed by progress in science. Scientific realism is the belief that the true nature of reality is the subject of scientific investigation, and while we may not completely understand it at any given moment, each experiment gets us a little bit closer. This is a popular philosophical position among scientists and science enthusiasts. A typical scientific realist might believe, for example, that fundamental particles exist even though we cannot perceive them directly with our senses. Particles are real, and their properties, whatever they may be, form part of the state of the world. A slightly more extreme view is that this state of the world can be specified with mathematical quantities, and these, in turn, obey equations we call physical laws. In this view, the ultimate goal of science is to discover these laws. So, what are the consequences of quantum physics on these views? As I mentioned above, quantum physics is not a realistic model of the world. That is, it does not specify quantities for states of the world. An obvious question is then, can we supplement or otherwise replace quantum physics with a deeper set of laws about real states of the world? This is the question Einstein first asked with colleagues Podolsky and Rosen, making headlines in 1935. The hypothetical real states of the world came to be called hidden variables since an experiment does not reveal them, at least not yet. In the decades that followed, quantum physics rapidly turned into applied science, and the textbooks which became canon demonstrated only how to use the recipes of quantum physics. In textbooks that are still used today, no mention is made of the progress in the foundational aspects of quantum physics since the mathematics was cemented almost 100 years ago. But in the 1960s, the most important and fundamental aspect of quantum physics was discovered, and it put serious restrictions on scientific realism. Some go as far as to say the entire nature of independent reality is questionable due to it. What was discovered is now called contextuality, and its inevitability is referred to as the Bell-Coken-Specker theorem. It was Bell's ideas and notions that stuck and eventually led to popular quantum phenomena, such as teleportation. Non-locality itself is wildly popular these days in science magazines, with reported testing of the concept in delicately engineered experiments that span continents and sometimes involve research satellites. But non-locality is just one type of contextuality, which is the real game in town. In the most succinct sentence possible, contextuality is the name for the fact that any real states of the world giving rise to the rules of quantum physics must depend on contexts that no experiment can distinguish. That's a lot to unpack. Remember that there are lots of ways to prepare the same experiment. And by the same experiment, I mean many different experiments with completely indistinguishable results. Doing the exact same thing as yesterday in the lab, but having had a different breakfast, will give the same experimental results. But there are things in the lab and very close to the system under investigation that don't seem to affect the results either. An example might be mixing laser light in two different ways. There are different types of laser light that, once mixed together, are completely indistinguishable from one another, no matter what experiments are performed on the mixtures. You could spend $1 trillion on scientific equipment and never be able to tell the two mixtures apart. Moreover, knowing only the resultant mixture, and not the way it was mixed, is sufficient to accurately predict the outcomes of any experiment performed with the light. So, in quantum physics, the mathematical theory has a variable that refers to the mixture and not the way the mixture was made. It's Occam's razor in practice. Now, let's try to invent a deeper theory of reality underpinning quantum physics. Surely, if we are going to respect Occam's razor, the states in our model should only depend on contexts with observable consequences, right? If there is no possible experiment that can distinguish how the laser light is mixed, then the underlying state of reality should only depend on the mixture and not the context in which it was made, which, remember, might include my breakfast choices. Alas, this is just not possible in quantum physics. It's a mathematical impossibility in the theory and has been confirmed by many experiments. So, does this mean the universe cares about what I have for breakfast? Not necessarily. But, to believe the universe doesn't care what I had for breakfast means you must also give up reality. You may be inclined to believe that when you observe something in the world, you are passively looking at it just the way it would have been had you not been there. But quantum contextuality rules this out. There is no way to define a reality that is independent of the way we choose to look at it. Talk about the famous double-slit experiment. If we cover one slit, the particles behave like tiny bullets, passing through the open slit and hitting the screen behind in a single band. But here's where it gets weird. When both slits are open, the particles create an interference pattern, like waves in water. It's as if each particle goes through both slits at the same time and interferes with itself. The plot thickens when we add detectors to observe which slit the particle actually goes through. The interference pattern disappears, and the particles act like bullets again. Next up, Schrödinger's cat. Schrödinger imagined a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the poison, killing the cat. If not, the cat lives. According to quantum mechanics, until we open the box, the atom is both decayed and not decayed. The cat is both alive and dead. And finally, quantum entanglement. When particles become entangled, their properties are linked, no matter the distance. Change the state of one, and the other instantly changes too. Einstein called this spooky action at a distance. So, does quantum physics deny reality? At the quantum level, particles don't follow the same rules as the macroscopic world. They exist in a realm of probabilities and possibilities, bizarre compared to our everyday experiences. It's not that reality is denied, but rather that it's far stranger and more complex than we ever imagined.